Hi, I'm Sering Chen. Today I present the research on an embedded true random number generator for FPGAs. FPGAs are widely used in cryptographic applications due to their flexibility and reconfigurability. However, generating high-quality random number on FPGA platform has been challenging. Many cryptographic operations, such as initialization vector, black patterns, and key generation, require truly unpredictable random numbers. A random number generator we call RGN is responsible for supplying this number, making it critical to cryptographic security. Weak RGNs can be exploited by attacks, leading to severe security breaches. And weak RGNs like an Netscape v2.0 can be exploited to break encryption. Thus, a robust true random number generator is essential for crypto strength. Our TRNG eliminates the need for PLLs by leveraging CLB-based jitter. The design achieves 0.5 megabytes seconds, bit generation with strong statistical properties, validated by NIST standard tests, providing a secure RGN solution for broader FPGAs architecture. Number generators come in two main categories: pseudo-random number generators and true random number generators. PRNGs are algorithm-based systems initialized with a seed value, producing deterministic sequence where the same seed generates identical outputs. In contrast, TRNG rely on physical random processes and operate without internal states, so their raw output may require bias correction to achieve true randomness. To optimize performance and security, hybrid systems combine both approaches by using TRNG outputs to periodically reset PRNGs, often implementing cryptographic hash functions like SHA-1 to ensure security while maintaining desired output rates. And the next part, I will discuss how FPGAs are used in cryptographic application and random number generations. FPGAs offer high encrypt speed, resource efficiency, real-time algorithm modification, and low development cost. And let's talk about period jitter. A key challenge in cryptographic FPGA designs is obtaining true random bits. Traditional methods include internal TRNG chips, which risk security vulnerabilities, or PRNGs, which lack true randomness. This research focused on extracting randomness from clock jitter, small variations in clock timing caused by semiconductor noise and environmental factor. The proposed method sample one clock signal using another slightly different clock, capturing bits from the jitter zone to produce random output. XOR operations are applied to enhance randomness. Unlike traditional design rely on PLLs for clock generation, this approach works on PLL-less FPGAs, making it more widely applicable. By using only configurable logic blocks we call CLBS, this design provides a cost-effective and secure TRNG solution for cryptographic applications. The proposed TRNG design utilizes ring oscillators to generate random bits. As shown in figure, the system consists of two independent and identically configured ring oscillator, a simple circuit, and a control circuit. The two ring oscillators COK0 and COK1 generate pulse stream with slightly different frequencies. The sampler unites COK0 to sample COK1, capturing variation caused by jitter. The output sequence consists of alternating rounds of 1 and gaps of zeros, and the length of each round in counted modulo 2 to produce a random bit. The control circuit manages the sampling processes, ensures stability and proper timing. The final output, RAM bit out, provides a stream of random bits with bit ready and red X signal indicating data availability. This design effectively generates true random bits using intrinsic Howard jitter, making it suitable for cryptographic applications without requiring additional internal components. Now let's look at the design and function of our ring oscillators, which serve as the core components of our true random number generators. As shown in this figure, the ring oscillator consists of a buffer, two transparent latches, and an inverter arranged in a feedback loop. The total propagation delay of these elements determines the nominal output frequency f of the oscillator, given by the formula, where pi represents the propagation delay of each element. Ensure a sufficiently high delay improves circuit stabilities. In ring oscillator CLB layout, we optimize the ring oscillator run at 115 MHz with a 3.3 nanosecond delay, ensures stable TRNG's performance. However, testing revealed intrinsic speed variation due to physical differences in CLBs. Additionally, CLB placement and temperature fluctuations impact oscillator performance. Understanding this factor is key to maintaining robust and secure randomness in traction in different conditions. Now let's examine the sample circuit, which plays a crucial role in extracting randomness from jitter in the ring oscillator signals. As shown in this figure, the D flip-flop uses the COK1 signal to sample the COK0 signal, capturing the cycle length variation caused by jitter. The S0 signal transition based on the sampled state of COK0. When COK1's rising edge samples the low portion of COK0, S-link switch to 0. And the next waveform. In this waveform, we see the waveform representation of this process. The C0 counter checks the number of COK1 cycles within an S0 signal period. By using the latest significant bit we call LSB of the S0 length, we convert the jitter variation into a random bit. This method effectively erect random variation in cycle length and represents them as a signal random bit, making it a simple yet effective approach for generating true random numbers without requiring prior knowledge of oscillator frequencies. Since the ring oscillators are designed identically, it is reasonable to assume they exhibit similar amount of jitter. However, if the frequency difference between the two clock signals, the COK0 and COK1 is too small, the S0 signal may transition multiple times before settling on a stable value. Without the control circuit, these small S0 cycles would be counted, resulting in corrected and non-random output. To adjust this, our control circuit enables the clock inputs only after a significant number of COK1 cycles have passed. Ensure that short and unstable S0 cycles are ignored. Additionally, the circuit disables the output flip-flops immediately after a random bit is latched, eliminating any correction between successive bits. An important secondary function of the control circuit is to prevent TRNG output when the frequency difference between the two ring oscillators is too large. If a jitter zone doesn't contain a valid sample, the control circuit ensures that the TRNG does not produce unreliable random bits. Oscillator speeds vary by up to 7% across FPGA CLBs and are affected by temperature impacting TRNG performance. And to adjust this, we use 4 independent ring oscillators sampled by a fifth, with XOR operation ensuring robust randomness. Tests across 7 FPGA locations show a 95% success rate, with only 4 intents for poor statistical properties. Increasing oscillator count and optimizing placement can further enhance TRNG stability and randomness quality. These pictures examine whether the jitter from ring oscillators produce true randomness. We consider the possibility that the apparent randomness might actually be a deterministic combination of two signals. To verify this, we built a sampling circuit to record the full length of S0 signal stream and analyze its statistical distribution. The left one illustrates the result using a pair of 113 MHz ring oscillators with a 35-piece frequency difference. The S0 signal cycle lengths exhibit 9 distinct values, confirming the presence of jitter includes randomness. The right picture shows the S0 signal distribution when the frequency difference was reduced to 22 pieces. The cycle lengths range from 322 to 342 cycles, centers around 332 cycles, forming a smoother distribution. This demonstrates that the variation in oscillator cycles, or jitters, is the underlying source of randomness in our TRNG. In the study, we identified biases in the output of our TRNG caused by 2 primary sources. The first one is limited bit length variation in the S0 signal and metastability in the sampling flip-flop. This factor introduces detectable deviation from uniform randomness, potentially compromising cryptographic security. To mitigate this bias, we exploit two well-known techniques. The first one is XOR reduction. This method XORs successive bits paired to reduce bias. For example, an original probability of 0.741 and 0.340 improves to 0.42 and 0.58 after XOR processing, bring the distribution closer to uniform randomness. And the second one is phenomenon corrector. This approach examines consecutive non-overlapping bit pairs, retaining the first bit if the pair is different and discarding both if they are the same. While this eliminates bias entirely, it significantly reduces the output rate and fails if bit correlation exists. Through testing, we observed no significant correlation in our output stream and opt for XOR reduction as our primary bias correction method. While bias reduction was performed in software for this study, future implementation aim is integrate these techniques directly into the hardware to enhance the robustness and security of FPGA-based TRNG. We discussed the bit generation speed of our TRNG. Since range oscillator frequencies naturally vary, our technique is designed to mitigate this issue by using the low-order bits of the S0 cycles as the random bit. This allows the system to function reliably even as the oscillator speed fluctuates. The output rate of TRNG depends on two key factors. The first one is the mean frequency of CLK first, and the second one is the difference in cycle times of the two ring oscillator, TC0 and TC1. The formula for the output rate is given by output rate. This method ensures that our TRNG maintains a stable bit rate despite oscillator frequency variations, optimizing randomness extraction for cryptographic applications. And the next part is testing the result. This table shows TRNG was tested on SLAAC 1-voltage FPGA test system, which includes 3 X-Lines Vertex XCV 1000 FPGAs and use Simplify V7.2 and X-Line ISE 4.2 to generate bit streams. To evaluate randomness, the research applied the NIST statistical test suite for random of pseudo-random number generators, which assesses the quality of the generated random bits. The NIST test suite calculates p-values, which indicate how closely the generated sequence matches an ideal random distribution. A p-value greater than 0.001 means the sequence can be considered statistically random. And the results show that our TRNG passed all statistical tests, confirming its ability to generate high-quality random number with no observed failures. The last part is discussion and conclusion. A conclusion is our TRNG design presents a valuable enhancement to FPGA-based cryptographic systems By fully integrating TRNG with FPGA without requiring special resources like PLLs, we improve security and design flexibility. Furthermore, our system includes a built-in failure detection mechanism, ensuring the output held when randomness extraction fail, making it a robust and secure solution for cryptographic application. And for this paper, I have two questions to discuss. First question is concern the reliability of jitter as a primary entropy source. While clock jitter is widely used for randomness extraction, its characteristics can vary significantly depending on FPGA models. Process variation, temperature fluctuation, and voltage change. How does the design ensure that the entropy remains significant under different operating conditions? Has the impact of environmental variation on entropy quality been quantitatively analyzed, and there any adaptive mechanism in place to compensate for entropy loss? And the second question is related to bias in the generated random bits and the effectiveness of XOR reduction as a correction method. While XOR successive bit pair help the balance to probability of 1 and zeros, it does not completely eliminate statistical dependency, especially in cases where bit sequences exhibit inherent correlation. Furthermore, XOR reduction reduces the effective output bit rates. Has the paper considered alternative bias reduction techniques, such as phenomenon correctors, entropy erection functions, or cryptographic post-processing? Would integrating a hybrid approach improve randomness quality while maintaining an efficient bit generation rate? And this is my reference paper. Thanks for your attention.